Alrighty, hello, we're going to do some solving exponential and logarithmic equations. What does that mean? That means we're going to look at problems where the variable is an exponent, or, so we have variable exponents here, and also when the variable is within our log, and we have a variety of strategies that we're going to do to accomplish that. Alright, and we're also going to look at some word problems. This looks really intimidating, but ultimately at its core, it is a simple process. So let's start with these two types of problems. These you might have seen in Algebra 1, and they don't require logarithms because they kind of have something convenient. The convenient thing is that 110 can both be, and 1/10 can both be expressed as powers of 10. So this is 10 squared, and this is 10 to the negative first. However, there were some other things in that equation, so we'll set that up like so. And we can combine using the power of a power property to call this 10 to the 2x equals 10 to the negative x minus or plus 3, negative times negative. And what's cool here is when our bases are the same, it's saying, all right, these two sides of the equation, if we need them to be the same, the exponents need to be the same. For lack of a better term, I'm going to just say that those are canceling out. And, oops, we'll add our x to each side. And what we get is 3x equals 3 and x equals 1. Now on this problem, again, we look at both of these and we have to think a little critically. We have to know our powers. You might use an exponent table, but we'll see if you do know them, like 5 squared is 25, 5 to the third is 125. We make that substitution. So this is a little different than what you might do for a lot of problems, which is like do something to each side of the equation. So the process is slightly different there. We still distribute. I'm going to go ahead, distribute and cancel out the bases all in one step just for the sake of space. So we get something like that. And, oops, I'm sorry, you know what? I had a little transcription error here. This is a 2. This is an x plus 2, so let's change that to a 2. Let's change this to a 6. And then we'll subtract 3x from each side, and we get x equals 6. But at its core, it's to get the bases the same by substituting something equal. And these are only set up that way by coincidence. When we look at part C, we have something that comes a little differently in that there's no power of 2 that's going to get us 7, because we have 2 squared is 4, and 2 to the third is 8. So I can at least expect my answers between 2 and 3. But what I can do is I can do log base 2 of 7 equals x. Rewrite it as a log. This now is the exponent isolated. I still can't quite put this in the calculator, but I could use the change of base formula, which is this, to take the base, put that one on bottom, that there. And these are now both base 10s. And this should be equivalent to whatever this is. And I can go ahead and put that in the calculator. So I'm going to open this up. A little preview for later. Log of 7. Close your parentheses, divided by log of 2. That closing of the parentheses here is really important. You'll get a lot of error messages if you don't do it. So we get 2.0, we'll just call it 2.81. Or 2.807, we'll call it there. 2.807. And we can verify our answer by doing 2 to the, and I'm actually going to go second answer. 7, perfect. So this problem here is talking about you're taking this dish, it's an Ethiopian stew, and you're taking it off the stove. You know its temperature, and we know the room temperature. So obviously it's going to cool down, right? And there's this constant that they just gave us. We would sometimes solve for this, but we're going to keep things simple. We're going to learn the base operation of, well, how do we deal with when we know this? And we're going to find when it's 100. So I'm going to break down this equation. Sometimes the equation looks a little different, but ultimately we'll use this model for this year. So this model, T is going to be our final temperature. T sub 0 is our, I always just say like object or the starting. The 0 is naught, which oftentimes refers to as a starting for anything in any math or science. R is going to be our room temp. The small r is, sometimes they call it a cooling constant. It has its own units. In this case, there was no units in there, so we're just going to say whatever units of time they're talking about. And those are all our variables. Remember, and we have t, small t is going to be our time, which is what we're going to solve for, okay? So again, the whole concept of this is a e to the negative, and what we're going to end up having is a graph. We're not actually going to need to graph this. Something cooling down, though, is going to kind of have, an exponential decay function with some asymptote, which will generally be, the asymptote will be the room temperature. So we're going to figure out when it's going to get to the room temperature or some other temperature. And to do that, we are going to use a log, but not quite yet. We're going to have to substitute everything in. So let's see what we got. We want this to be 100 degrees. So we're going to say our final temperature is going to be 100. Our starting is 212. Our room is 70. It gave us the root r, this small r here. And we don't know this. This is what we're looking for. So let's set this up. We have 100 equals 212 minus 70 e. Don't forget the e. This is a really easy one to forget there. Minus 6t plus the room temperature, which is 70. This little plus 70, again, if you're thinking about the model, it's like, well, we're never going to get lower than room temperature. We're always going to approach the room temperature. All right, so if something was heating up, I guess it would approach it going up. All right, so we got 100 equals, and we're going to continue through that. I had some notes on this one ready to go. 142 e to the negative 0.046 t plus 70. And so at this point, what I'm trying to do right here is I'm trying to get this part by itself, okay? So I'm going to use order of operation. I'm going to isolate. I'm going to think about getting that by itself by subtracting 70, which then gives me 30 equals 142 e to the negative 0.046 t. And we divide by 142. And at this point, I'm actually not even going to simplify this fraction. We'll leave it like this. We actually have an operation that will get, and there's two ways you can look at this. I like this personal one. This is one of the best. If I wanted to cancel this e out, if I did ln, the natural log, which if you recall, hopefully you recall, is log base e, ln and e will invert each other. They'll cancel out, but I can't just do it to one side. I'm going to do it to both sides. And on this side, it will cancel out. They will invert each other. And so what we end up with is ln of 30 over 142 equals negative 0.046 t. And notice I still haven't put this in the calculator yet. I will, but I like to do it at the end so we don't have any rounding issues, which you might run into. And what we'll do is we'll go ahead and we'll get this in the calculator. So what does that look like on the calculator? I'm going to hit my ln. I'm literally putting all of this in the calculator at once. I'm going to close my parentheses here, divided by that negative. Make sure you use a negative, not a subtract button. That sometimes happens. And we get 33 let's call it 33.8. I don't know if that's minutes or seconds. There's just some time units, depending on what we're talking about. I want to emphasize this step is the step that's unique to this unit. This is really the function. How do we get something out of the exponent? Well, we can use something like a natural log if we have a base e. If we had a base 10, we would just use common log. And if we had a different log, we would, we'll look at that. So this seems like a pretty obvious, and I'm just going to demonstrate. It's basically saying if we have the same log on each side, and it's just the side for side, it's very analogous to this, they will cancel out. Because we're saying, hey, each side needs to be the same, right? So in this, it's good to just say, hey, these ln's are going to cancel out. Because if I wanted both sides to be the same, then boop, the insides need to be the same. And at that point, we can go ahead and solve this like a normal problem with just some basic algebra steps. Like so. But what about this? There's no log on each side here. There's two ways about this where we can think about it. Both will get us to the same spot. We could rewrite this as an exponential. So if you recall, I'll write this all the way over here. We have a reformatting strategy. You might use different letters than I do, and that's totally cool. But these are equivalent. And what's cool is that whatever is in the inside, I know I used an X here, but whatever is in the inside, we can kind of get to a different spot to the other side by putting in an exponential. So if we ever see a variable in here, it often means that let's reformat it, and we can get that variable outside of the exponent. If you need, or outside the log, I'm sorry, if you like having an operation to do on both sides, and that's how your brain works a little better, there is an operation that we're doing, and it's called exponentiation. It's really fun to say. And it's saying, well, I want this log base 2 to cancel out, so I need to do a 2 to that, but I'm going to do that. So we make the problem the exponents. It's reverse of what was doing over here. And ultimately, this would cancel out, and we would just be back to this step right here. We'd have, 5x minus 17 equals 2 to the third. So I'll finish solving this problem. Again, that operation I just did right there was called exponentiation. It's one of my favorite words to say. I don't know why. It's very satisfying to say off the tongue. Exponentiation. And let's finish off this problem. So we get 8 plus 17. Get 25 equals 5x. X equals 5. Right. Well, we have multiple logs here, but they're not on opposite sides, and if I move this to that side, I kind of am stuck a little bit. So one way, though, we can condense this into one log using the product property. Since this is a plus right here, we can multiply those two. So I'm going to say log of 2x squared minus 10x equals 2. Again, I multiplied 2x, distributed in there. Again, this is log base 10. It's a secret 10 because it didn't say 1, so we assume it's log base 10. And then I'm going to, again, use the strategy of thinking of it as a, rewrite it as an exponential. And I see I have a quadratic here, like I can't combine these, and so we're at the point in algebra where oftentimes we will learn a set strategy, but we should also be ready for any of the other math that we previously learned to maybe come and play a bit. All right, so that's going to occur more and more. So the math I'm doing right now is I am factoring. I factored out a 2, and this is a simple factor, meaning coefficient of 1. So here is, oops, I forgot to factor out the 2 from every term, right? So if negative 50, negative 5, that becomes negative 10 and positive 5. So my factorization is 0 equals 2 times x minus 10 and x plus 5. My two solutions are x equals 10 and x equals negative 5. Now, these are great. One of the things we have to look for, and as I look here, I'm going to start noticing a problem. We want to check if any errors are going to occur. If you recall, logs, when I look at this format here, right, this a, if this base is positive, a is always going to be positive. And that's really important to remember. So the concept I'm going to explain just one more time is that, like, for example, if I had something like this, 10 to the x equals a is always going to be greater than 0. The graph of that function even would be, an asymptote at 0. There is no exponent that will create a to be negative. And that includes right here. So what I'm going to look at is what happens when I plug these numbers into my original equation. Would I get any negatives up there? So if I plug 10 in here, I get log base 10 of 5, which is fine, right? So I can check that. I'm going to check this log right here. I say log base 10 minus 5. Let's say log of 5. And that's fine. That's totally cool. As long as this is positive, that's totally cool. And I would get the same positive number, a different positive number, but I'd get a positive there. But look here. If I plug this into this, if I get just, and I can just have to look at one part because I don't have to look at both, but if there's a part where an error will occur, meaning a negative number, this is an issue. Log base 10 of negative 10. If there's a part that's not going to work, meaning not give us a solution, we can even see in our calculator, look at this. Log, I don't have to put 10 because there's log base 10. It's going to say domain error because, well, there's, like I said before, there is no power. This will never be true. There's no solution to this, which that is ultimately the same thing as what that's saying. So we're going to go ahead and cross this out, and we're going to say that solution is extraneous. That just means, like, mathematically everything I did was correct, but it didn't work in the logistics of this problem. So go ahead and you're welcome to do the practice problems. You can see here we'll change the bases here. Hint, hint, negative exponent on this one. You will need to use the change of base formula at some point and a calculator for that one. Logs will cancel out here. You might need a condense, and I'm looking here, it looks like you might even need a factor on this one. Don't let the ln kind of scare you too much. You still can condense. You're going to remember that you might have a base of e at some point. And again, as a little hint, instead of factoring, because I'm assuming you're going to have a decimal number here as one of the constants, the quadratic formula will be particularly useful here.